Welcome to this lesson on momentum in isolated systems. We are actually going to begin by reviewing the notes from the previous lesson. So if you don't have those out yet, please find them. In the previous lesson, we rearranged Newton's second law to obtain this result, which tells us that the net external force on a system times the time interval that force acts is equal to the change in momentum of the system. And then at this part here is the definition of impulse. We further rearranged this to find what we call the momentum principle, that the initial momentum of the system plus the impulse from the net external force on the system equals the final momentum of the system. We can see from this that if the impulse is zero, then the initial momentum will be equal to the final momentum. After that, we began example 3, where our friend Justin Case is on a skateboard. He pushes on a ball. Because of Newton's third law, we know the ball pushes back on him. And we analyzed this for the system definition of just being the ball in the system. What we're going to do today is we are going to do 2 more different systems. So we will define the system as Justin with the skateboard, and then in part C we will define the system to be the ball and Justin with the skateboard. So we're going to put all of those objects into the system. What we found last time, just to review what we worked on, was we found that the impulse on the ball was the external force on the ball, which was the force of Justin and the skateboard on the ball, times the time interval. So we got an impulse of +8. And then we found, using the momentum principle, we found that the final momentum of the ball was +8 Newton seconds. And then we used the definition of momentum, mass times velocity, to find the final velocity of the ball, which was +2 meters per second. And our momentum bar chart shows the ball started with an initial momentum of 0. It experienced an impulse of +8 Newton seconds, which changed its momentum by that amount, and the final momentum was +8 kilogram meters per second. So now pause the video, complete part B on your own, and when you've finished, come back. Welcome back. Hopefully you saw that there is a net external force on the system because the ball pushes on Justin with the skateboard to the left. And because there is a net force on the system, the momentum will change because there's an impulse. So net force causes an impulse. That impulse causes the momentum to change, so the momentum is not constant. Check your work to see that you found an impulse of -8 Newton seconds, a final momentum of -8 Newton seconds or kilogram meters per second, and a final velocity of -0.12 meters per second. Your bar chart should show an initial momentum of 0, an impulse of -8 Newton seconds, and a final momentum of -8 kilogram meters per second. If you have questions on any of this and would like to see this part worked out in detail, that is provided at the end of this lesson video. Before we go into part C, I'd like to take a closer look at these 2 bar charts that we have for part A and for part B, for these 2 different definitions of systems. Notice that the sign of the impulse is opposite, but that the amounts are the same, so +8, -8. And then also look at the final momentum. +8 kilogram meters per second and -8 kilogram meters per second. It almost looks like if you added these together, you would have a total impulse of 0, and you would have a final momentum of 0. That is very interesting. Let's do part C now and find out what's going on with momentum and impulse for the system if the system includes both the ball and Justin with the skateboard. Defining the system this way, what forces are external? So looking back at our diagram, if we have now both objects included in the system, what forces are external? Well, The normal force is external. Both normal forces are external because they're caused by the ground, and the ground is not in the system. I should draw the system oval more like that to not include the ground. Force of gravity is external because that's caused by an interaction with the Earth, and the Earth is not in the system. But these forces, the force of Justin and the skateboard on the ball and the force of the ball on Justin and the skateboard, those are internal because those are forces resulting from an interaction with another object that's inside the system. So our external forces are going to be both force of gravities and both normal forces, but not the force between the ball and Justin with the skateboard. Now, is there a net external force? Well, thinking back again to the free body diagram, we know that this force of gravity balances out that normal force, so no net external force there, and that these vertical forces are also balanced, so no net external force from those. So these are all going to cancel each other out when they're added together as vectors. So the net external force in the system is no. So now, is the momentum of the system constant? Well, let's see. If the initial momentum plus the impulse equals the final momentum, and there is no net external force, then there is no impulse, because the impulse is the product of the net external force times the time interval. So now we can see that the momentum will be constant, and we're going to hopefully see that in this example. Okay, we are looking for the impulse on the system, the final momentum, and the final velocity. So the impulse on the system in the x direction is going to be that net external force. I'm just going to write it this way. It will be an average if it's a force that changes with time, times the time interval. Well, we know that the net external force is 0 because there is none. So this is 0, so the impulse is 0. Now let's find the final momentum. Actually, before we do the final momentum, let's find the initial momentum. Just because then we can see how to do that when there's more than one object in the system. So to find the initial momentum of the system, what you have to do is you have to just add together the initial momentum of each object in the system. So the initial momentum of the ball plus the initial x momentum of Justin and the skateboard. Well, we know they're both at rest, so the mass of this one times the velocity of the ball initially is 0. The mass of Justin and the skateboard times the velocity of Justin and the skateboard beforehand is also 0, so we get 0 kilogram meters per second. Now let's find the final momentum of the system that includes both of those objects. So the final momentum of the system is the sum of the final momentum of each one. So the final momentum in the x direction of the ball plus the final momentum in the x direction of Justin and the skateboard. And we found these values already in A and B. So the final momentum of the ball was +8, and the final momentum of Justin and the skateboard was -8. So +8 and -8. So adding these together, we get 0. For the final momentum of the system. So notice final momentum is 0, but things are moving, right? And that's because these have signs, because they are vector quantities. This object is moving, but it has a negative sign. And we notice that the initial momentum is equal to the final momentum. Final momentum is equal to the initial momentum. So we are seeing here that the momentum is constant. Okay. let's draw the momentum bar chart for our system. So draw the vertical axis, the horizontal axis, and how are we going to do this when we have more than one object in the system? Well, what we do is just draw a bar for the momentum of each object before and a bar for the momentum of each object afterwards. So the first bar will be the initial x momentum of the ball, and the next bar will be the initial x momentum of Justin and the skateboard. The next bar will be the impulse on the system, and then we get to the final momentum. So the final momentum of the ball and the final momentum of Justin and the skateboard. So the initial momentum of the ball was 0, so no height for that bar. The initial momentum of Justin and the skateboard was also 0. The impulse on the system was also 0 because the net external force was 0. But the final momentum of the ball, it was moving afterwards. So final momentum of the ball was positive 8 kilogram meters per second. And the final momentum of Justin and the skateboard was negative 8. So I'm going to put the little dashed boundary around the impulse. So we can see, if we think about the whole system, that with both the ball and Justin and the skateboard included in the system, the total momentum beforehand of the system is 0. And then afterwards, including both in the system, the final momentum is 0. So we see momentum is conserved. One additional thing we were supposed to find in parts A, B, and C of example 3 was the final velocity of the system. And we did that when the system was just the ball. We did that when the system was just Justin with the skateboard. But in this situation, what are we going to do to find the final velocity? Because we have more than one object moving afterwards. So what does it even mean to find the velocity of a system that includes more than one object that's moving? Well, this is a question we're just going to park for now and hopefully come back to next week. All right, what are the key ideas? First of all, what is an isolated system? A system is isolated if the net external force on the system is 0. That is the definition of an isolated system. The net external force on a system will be 0 if one of two things happens. Either there are no external forces at all on the system, or there are external forces, but they add up to 0. And that's the situation that we had up here. There were external forces, but they added up to 0. Number 2, what is true about the net impulse on an isolated system? The net impulse on an isolated system is always 0. This is because from the definition of impulse, we have that net impulse is equal to the net external force times the time interval. This is just the definition of impulse. And then since the net external force is 0, the net impulse must also be 0. So if the net external force is 0, then 0 times any time interval is going to give you 0 for the net impulse. 3, what is true about the momentum of an isolated system? The momentum of an isolated system is constant. Another way of saying that is it does not change. Another way of saying that is it is conserved. So a lot of times you will hear the phrase conservation of momentum, just meaning that the momentum is staying constant. And why is this true? Why is the momentum of an isolated system constant? Well, from the momentum principle, we know that the initial momentum, this should be vectors, equals the final, the initial momentum plus the impulse on the system equals the final momentum. And then, since the net impulse on the system is 0, which is this item, you can see then that the initial momentum must equal the final momentum. So it's all dependent on that impulse being 0, because it's the impulse that changes the momentum. Number 4, how can the momentum principle be applied to systems that include more than one object? So that's what we did in example 3C, was we did apply it to a system that had more than one object in it. And this just formalizes what we did into an equation form. So as vectors, we can write the vector equation that the initial momentum of the system plus the impulse on the system equals the final momentum of the system. And usually we will use this momentum principle in component form. So I've written it here for the x component direction, but you can just replace x with y or z to get an equation for the other ones. But this is not an equation you need to memorize, because as you'll see in a moment, it's basically all you really need to know is this overall equation. Because if you look at this term right here, m1 times the initial velocity of object 1, this is just the initial momentum of one object. This is the initial momentum of the second object, and then you would just add in the initial momentum of however many more objects you have. So all of this just means add up the initial momentum of every object in your system. This is the impulse, and then over here you can see this is the final momentum of the first object plus final momentum of the second object plus the final momentum of all the other objects in your system. So all of this is just adding up the final momentum of every object in your system. So you can see initial momentum of the system, just add up all the initial momentum of each object. There's the impulse, and then this is just adding up the final momentum of each object, just as we did in example 3C. And that concludes the lesson on momentum in isolated systems. Okay, in part B, we're defining the system as Justin with the skateboard. And we're always going to need to consider what the external forces are. So for Justin and the skateboard, this is our system. And the external forces are any force that results from an interaction with an object outside the system. So the normal force is an interaction with the ground. The ground is not in the system, so that's an external force. This is caused by an interaction with the ball. The ball is outside the system, so that's an external force. And then force of gravity, because the Earth is outside the system, that is an external force. So we have 3 external forces. We have the force of gravity on Justin and the skateboard. We have the normal force on Justin and the skateboard, and we have the force of the ball on Justin and the skateboard. So those are the external forces. Now we need to know what is the net external force on the system. Well, looking at the free body diagram, we can see that the vertical forces are balanced. So if you add up those vectors, you'll get 0 because there is no acceleration vertically going on. So these two cancel out, and we are left with only the force of the ball on Justin and the skateboard as our net external force. So yes, there is a net external force. Is momentum of the system constant? Well, we know from the momentum principle that if there is an impulse, then the momentum will change. Initial momentum plus impulse is final momentum. So there is an impulse because impulse is this force times the time interval. Is the momentum constant? No. We are looking for the impulse and the final momentum and the final velocity of Justin with the skateboard. So to find the impulse, that is J in the horizontal direction, and that's going to be the force times the time interval. Well, the force that's acting is just this horizontal force of the ball on Justin and the skateboard times the time. The force is -8 newtons. Really watch out for signs when working with momentum and impulse. So -8 newtons, and the time was 1 second. So the impulse is -8 Newton seconds. The negative means that the force was exerted in the negative direction. Okay, now we need the final momentum. We are going to start here with our momentum principle. So we have the initial x direction momentum for Justin and the skateboard plus the impulse on Justin and the skateboard equals the final momentum of Justin and the skateboard. Now the initial momentum is going to be the mass of Justin and the skateboard times the initial velocity, which the rest, so this is 0. The impulse we just found, -8 Newton seconds, and now we can find the final momentum. This whole term is 0, so the final momentum of Justin and the skateboard is -8 Newton seconds. And lastly, let's find the final velocity of Justin and the skateboard. So the final velocity is going to come out of this final momentum term. So I'm going to continue on here. 8 Newton seconds. This final momentum is the mass of Justin and the skateboard times the final velocity of Justin and the skateboard. So I need to substitute the mass, which is 65 kilograms, and dividing both sides by 65 kilograms, we find that the final velocity of Justin and the skateboard is -0.12 kilogram meters per second. When you get to a result, very wise to go back and look at your diagram and see if it makes sense, especially the sign. So we expected that Justin and the skateboard would be moving to the left afterwards, and now we know that that velocity is -0.12 meters per second, which allows me to catch my error here. This should be meters per second. The last step is to draw the momentum bar chart. So we have our vertical axis, our horizontal axis. The horizontal axis has no units in a bar chart, so the width of your bars doesn't matter. So this is going to be the initial momentum. I'm just going to put in the subscripts of Justin and the skateboard, the impulse on Justin and the skateboard, and the final momentum of Justin and the skateboard. So initially there is 0 momentum because Justin and the skateboard are at rest. Then they experience an impulse of -8 Newton seconds. That is the impulse, which caused the momentum of the system to change. And the amount that it changed by is the amount of the impulse. That is exactly equal to the change. So then the final momentum that we found was -8 Newton seconds. You could also use units here of kilogram meters per second. I'm going to use kilogram meters per second here. Okay, they were initially at rest, experienced an impulse of -8 Newton seconds, which changed the momentum by that amount, giving them a final momentum of -8 kilogram meters per second.